Close your eyes for just a moment and imagine the world before quantum physics, a place where certainty felt like gravity, where everything moved in predictable paths, and where the universe behaved like a grand, unshakable clockwork. What if I told you that beneath this ordered surface, reality itself was whispering secrets, waiting to be unraveled? Tonight, we step into a quiet revolution, one that began not with a thunderous declaration, but with a single, hesitant question: what if the universe doesn't always behave the way we expect it to? This is not just a story about equations or hidden forces, it's a journey into the heart of what makes existence strange, beautiful, and deeply connected. We'll explore how a simple observation about glowing fireplaces shattered the idea of a perfectly predictable world. We'll meet the physicists who dared to listen when the universe spoke in riddles, and we'll uncover how something as ordinary as light became the key to unlocking a new understanding of reality. But most importantly, we'll learn why this strange world of quantum physics isn't just for scientists or scholars. It's a lens through which we can see the hidden poetry in everything around us. Picture this: you're sitting in a cozy room, the kind where the air hums with warmth, where the edges of reality feel soft and familiar. Now, imagine if someone told you that the very act of looking at something, whether it's a cup of coffee cooling on your table or the shadow of a tree outside your window, could actually change it. Not because your mind has power over the world, but because the universe itself is made of possibilities waiting to be chosen. That's the magic and the mystery of quantum physics. And tonight, we'll wander through it together, not as students memorizing facts, but as dreamers ready to feel what it all means. Let's begin where it all started, in a world that thought it had everything figured out. For centuries, the rules of physics were as solid as the foundation of a house. Isaac Newton had mapped out the path of every falling apple, every orbiting planet, every thrown stone. The universe was a machine, its gears turning with perfect precision. If you knew where something was and how fast it was moving, you could predict its future forever. It was a comforting thought, wasn't it? A world where nothing was left to chance, where everything followed a path already written in the stars. But then came the fireplaces. Not the warmth, not the crackling, just the light. Physicists of the late 19th century looked at glowing embers and saw a problem. According to the rules they trusted, a hot enough object should have blazed with an endless flood of invisible ultraviolet light, scorching everything in its path. Yet that's not what happened. The glow was gentle, shifting from red to orange to white, as if the universe itself were holding back. This was the ultraviolet catastrophe, a puzzle wrapped in a paradox, a crack in the foundation of their understanding. The equations they relied on were failing at something as simple as explaining why a stove doesn't turn your kitchen into a furnace of invisible rays. Enter Max Planck, a man whose quiet persistence would change everything. In 1900, he made a suggestion so radical that even he struggled to believe it. What if energy didn't flow like a river, smooth and endless, but instead came in tiny, indivisible drops? He called them quantalittle packets of energy, like coins rather than a flowing currency. At first, it was just a fix, a band-aid on a broken equation. But Planck's idea was the first domino to fall. It whispered that the universe might not be as seamless as it seemed. Then came Albert Einstein. A few years later, he took Planck's hesitation and turned it into a revolution. He was studying something called the photoelectric effect, light hitting metal and freeing electrons. According to the old rules, brighter light should have always worked. But that wasn't what experiments showed. Instead, it was the color of the light that mattered. Dim blue light could free electrons, while even the brightest red light often couldn't. Einstein's solution: light wasn't just a wave, it was also made of particles. Little bundles of energy he called photons. Imagine sunlight as a shower of golden coins, each carrying just enough energy to nudge an electron free. Red coins were too light to do the job, No matter how many you had, blue coins, though fewer, carried the weight to open the door. This wasn't just a theory, it was a revelation. Light was both a wave and a particle, depending on how you looked at it. The neat categories of physics were blurring, and the universe was revealing itself to be far stranger than anyone imagined. Today, this idea powers the solar panels on rooftops, turning sunlight into electricity. Every time the sun charges your phone, you're witnessing Einstein's photons at work. A quiet puzzle solved in 1905 became the foundation of technologies we now take for granted. So why does this matter to you? Because this story isn't just about science, it's about wonder. It's about the moments when the world feels alive, when the ordinary suddenly becomes extraordinary. Quantum physics teaches us that reality isn't just one thing, it's a tapestry of possibilities, woven together by the act of observation. It's in the way your coffee cools, the way shadows dance, the way music swells and fades. These familiar moments are little doorways into the quantum world, inviting us to see the hidden magic in the everyday. Tonight, we'll walk through that door together. We'll follow the path from Planck's reluctant quanta to Schrödinger's famous cat, from Heisenberg's uncertainty to the entangled particles that seem to communicate across impossible distances. And we'll do it not with cold equations, but with stories that remind us why science is more than facts and figures. It's a way of seeing the world with new eyes. So take a deep breath. Let the room around you feel safe, familiar, because the journey ahead isn't about memorizing theories, it's about feeling the wonder of it all. The universe has been whispering its secrets for centuries. Now, it's your turn to listen. Close your eyes for just a moment and imagine this light, not as the smooth, unbroken glow we see every day, but as something far more delicate, far more alive. Picture it as a shower of tiny golden coins, each one carrying just enough energy to nudge an electron free, to spark a reaction, to whisper the secrets of the universe itself. This isn't some abstract idea pulled from a textbook, it's the quiet revolution that reshaped how we see reality. It's the story of how two brilliant minds, Max Planck and Albert Einstein, stumbled upon a truth so profound that it would unravel the very fabric of classical physics. Max Planck was a meticulous man, the kind who measured the world in careful increments. He wasn't looking for a revolution, was just trying to make the numbers add up. When he studied the glow of heated objects, the equations refused to behave. The classical rules of physics couldn't explain why certain colors of light appeared more vividly than others. So, in a move that felt like a last resort, he proposed something radical. Energy wasn't flowing freely like a river. It came in tiny, indivisible steps, like climbing a staircase instead of walking up a ramp. Each step was the same height, determined by a constant so small it seemed almost invisible. He called it Planck's constant, a number that would later become the foundation of an entirely new way of understanding the world. At first, Planck thought his idea was just a temporary fix. But Einstein saw its potential. He asked a simple question: what if light itself was made of these packets of energy? If energy could only exist in discrete amounts, why couldn't light? He called these packets photons, tiny bursts of pure light, each carrying energy based on its color. A red photon was gentle, like a drop of rain. A blue photon was sharper, carrying more force. And when light hit a metal surface, the electrons didn't respond to brightness alone. They only broke free if each photon carried enough energy to pay the price. Brightness didn't matter if the individual coins were too small. 1 billion pennies couldn't buy what one golden coin could. This wasn't just theory, it was an experiment waiting to be proven. And when it was, the implications shook the world of physics to its core. Light wasn't just a wave spreading through space. It was also a particle, a shower of energy packets, each one carrying a piece of the universe's hidden rhythm. The photoelectric effect, once a puzzling anomaly, became the key that unlocked a new door. Einstein's explanation was so precise that it earned him a Nobel Prize. But more than that, it changed everything. For the first time, scientists saw that reality wasn't smooth or continuous. It was made of steps, of drops, of quantitany, indivisible pieces that defied the old rules. Here is the truly astonishing part: this dual nature of light wasn't an exception. It was a rule. When scientists sent light through two narrow slits, it behaved like a wave, creating patterns of interference ripples overlapping like water in a pond. But when they looked closely, they saw something else. Light arrived in individual hits, like particles knocking on a door. It wasn't that light changed its mind. It was that nature insisted on wearing both costumes at once, wave or particle, depending on how you asked the question. This wasn't just a quirk of light, it became the first great signature of the quantum world. Even matter, the solid, unyielding stuff of our everyday lives, carried this same duality. Electrons, atoms, even entire molecules could behave like waves under the right conditions. The larger the object, the harder it was to see this ghostly behavior. But it was always there, humming beneath the surface of reality. So imagine this: the world isn't made of smooth, endless flows of energy. It's made of notes, of droplets, of packets so small they seem almost invisible. Turn on a lamp, and you're not just seeing a continuous glow, you're witnessing a river of photons, each one carrying a fixed amount of energy, determined by Planck's constant. The brightness isn't a smooth fade, it's the number of these tiny bursts increasing or decreasing. The universe isn't carved out in infinite gradations. It's made of steps, of rhythms, of the smallest possible beats to the drum of existence. And that rhythm, it's set by a number so tiny it's almost imperceptible, yet so fundamental that it governs the very fabric of reality. Now, let's bring this down to something even more personal. You're lying here, listening to your breath, feeling the weight of your body against the bed. The air around you is made of atoms, stable and unchanging for billions of years. But deep down, those atoms aren't little solar systems with electrons orbiting like planets. There's something stranger, something more alive. Niels Bohr, a young physicist with a sharp mind, realized that electrons couldn't orbit just anywhere. They were restricted to specific energy levels, like rungs on a ladder you can't step between. You can't stand halfway. You must be on one step or the next. This wasn't just a mathematical trick. It was a law of nature. The old picture of the atom, so neat and orderly, collapsed under the weight of this new truth. The electrons didn't spiral inward and disappear. They leapt from one energy level to another, releasing or absorbing photons in the process. It was as if the universe itself was made of discrete notes, of jumps rather than smooth transitions. So why does this matter to you? Because this story isn't just about science, it's about wonder. It's about looking at the world and seeing something deeper, something more alive than we ever imagined. The light from your lamp, the warmth of your breath, the very air you're breathing, all of it is woven from these tiny, indivisible pieces. The universe isn't a machine with predictable gears. It's a symphony of probabilities, of possibilities, of energy leaping in steps we can barely perceive. And yet, here you are, part of it, listening, understanding, just as Planck and Einstein once did. Let this sink in the next time you turn on a light. Remember that you're not just flipping a switch. You're unleashing a shower of photons, each one carrying the echo of a revolution. The world is made of packets, of notes, of quantitany bursts of energy that remind us reality is never as simple as it seems. And in that understanding, there's a quiet kind of magic. The universe isn't smooth. It's stepping, leaping, vibrating with life at its smallest scales. And you, right now, are part of listening to its rhythm. So picture this: the universe isn't just a smooth, flowing river of energy, but a cascade of tiny, indestructible droplets, each one carrying its own unchangeable story. When you turn the light on in your kitchen or dim the lamp beside your bed, you're not just flipping a switch, you're unleashing an army of these invisible messengers, each one a fleeting spark of a revolution that happened over a century ago. Countless photons, born from the fire of atoms, are racing toward your eyes right now, carrying with them the quiet whispers of Niels Bohr and Albert Einstein. They're the living proof that reality isn't made of endless divisions, but of discrete notes, like the keys on a piano that only play certain tunes. There's a rhythm to it, a smallest beat, a fundamental graininess to existence that says, no, you can't keep cutting the cake forever. At some point, the pieces stop splitting, and what you're left with is the elegance of the whole. Imagine, for a moment, holding a tiny model of the solar system in your hand's planets circling a sun, each one tracing its path with perfect precision. For centuries, this was how we thought of everything, even the unseeable world of atoms. We imagined electrons orbiting their nuclei just as planets orbit stars, a miniature cosmic dance of perfect harmony. But then, one by one, the experiments began to show us that this elegant picture was missing something critical. If electrons were tiny planets, they should have spiraled into their nuclei long ago, collapsing atoms in the blink of an eye. Instead, the universe held steady. Your body, the air you breathe, the stars that light the night sky, they all depend on atoms that refuse to unravel. Something was holding them together, something we couldn't see yet. In 1913, a young physicist from Denmark named Niels Bohr stepped forward with an idea that would rewrite the rules. He suggested that electrons don't drift freely like planets, they're trapped on rungs of a ladder, each step a fixed energy level they must occupy. You can't stand halfway between two rungs, just as you can't play a note that doesn't exist on a piano. When an electron jumps from one rung to another, it doesn't glide smoothly, it releases a burst of energy in the form of a photon, a single packet of light. And that photon, that tiny spark, carries with it the color, the signature, of the atom itself. Look at the glow of a neon sign, the shimmer of a distant star, the flicker of your computer screen. They're all echoes of electrons climbing and descending their quantum staircases, playing their loud notes in the grand symphony of the universe. Bohr's model wasn't just a scientific breakthrough, it was a poetic one. Suddenly, the mysterious scribbles of light in a spectroscope weren't random chaos, they were the fingerprints of atoms, the scales and harmonies of a hidden music. The world wasn't infinitely divisible, but made of discrete steps, of packets of energy that couldn't be split further. It was as if nature itself had a menu, a set of allowed options, and everything beyond that was simply not permitted. This discreteness, this quantized world, is the heart of quantum theory, a reminder that reality isn't a smooth, unbroken tapestry, but woven from the smallest pixels of energy, from the tiniest, unchangeable beats. So let's bring this closer to home. Think of a child at a playground, climbing up a slide. They can stop at the first rung, the second, the third, never in between. When they step down, each drop releases a little burst of energy, like a spark catching the light. Now imagine that instead of laughter, each step down produces a photon, a tiny flash of color, a note in the spectrum of the world. The playground is the atom. The ladder is the energy levels, and those sparks, they're the light we see in fireworks, in neon signs, in the stars. Every time you look at a glowing screen or pass beneath a street lamp, you're witnessing electrons leaping between these quantized rungs, playing their allowed notes in the grand composition of existence. And here's the beautiful part, this isn't just abstract science. It's the foundation of the technologies that shape your world. The screens you watch, the lasers that scan your purchases, the fluorescent lights that illuminate your home, they're all orchestrated by electrons climbing and descending their quantum staircases. When you see the red glow of a neon sign, you're looking at atoms excited by electricity. They're electrons jumping up the ladder and then falling back down, releasing their energy as light. The familiar colors of the universe, from the blue of the sky to the violet of twilight, are the fingerprints of these quantum leaps. Bohr's insight wasn't just about atomsit, was about the very structure of reality. It told us that stability, that quiet certainty that the world holds together, isn't an accident. It's built into the fabric of things, into the rungs of the ladder that electrons must climb. So close your eyes for a moment and let this image wash over you. Picture an electron, a tiny musician on a piano with only a few allowed keys. It jumps from one note to another, and with each leap, a photon is born, carrying the color of the universe. The air you breathe is made of these atoms, these stable, quantized structures holding together for billions of years. The light that touches your face, the warmth of the sun, it's all part of the same symphony, the same great composition where even the smallest steps create the most beautiful harmonies. And if all of this feels strange, if it makes you pause and wonder, you're in good company. Bohr himself said that anyone who isn't shocked by quantum theory hasn't truly understood it. Because here's the thing, the universe isn't just weirder than we thought. It's weirder than we can think. It doesn't wait for us to catch up. It doesn't care about our intuition. It operates on rules that defy the smooth, predictable world we've built in our minds. And yet, in the quietest way, those rules give us order. They tell us that even in the tiniest corners of existence, there is structure, there is harmony, there is a rhythm that holds everything together. So tonight, as you lie back and let these thoughts drift through your mind, remember this: the world is both stranger and more beautifully ordered than it appears. The stability of your body, the steady glow of the stars, the colors of the sunset, they're all echoes of electrons dancing on their quantized rungs, playing the allowed notes of the universe. And if your eyes grow heavy, if the image of glowing sparks and climbing ladders carries you into rest, let it. Because in the gentle framework of quantum theory, even the smallest steps create the greatest symphonies of existence. And you, right now, are part of that music. So let me tell you something extraordinary, because the universe isn't just waiting for us to catch up. It's rewriting the rules while we're still trying to figure out the first chapter. The moment you think you've got a handle on reality, it slips through your fingers like mist. Now, picture this: you're watching two slits, just like the ones in your old physics textbook. But instead of marbles rolling through, you're firing single particles of light photons at a time. No crowd, no rush, just one lonely photon at a time. What do you expect? Maybe two neat little piles on the other side, right? A little heap by each slit, like you'd see with pebbles. No, something else happens. Over time, those photons build a pattern of stripes, not piles. Not dots, stripes. The kind you'd see if you dropped waves into water. The kind that prove these particles are behaving like ripples. But here's the kicker: even when you fire them one by one at a time, they still act as if they're interfering with themselves. As if each photon is somehow slipping through both slits at once, like it's shy and won't commit to a single path until you look. The scientists watching this experiment must have felt like the ground was shifting beneath them. It wasn't just that the results defied expectations. It was that reality itself seemed to hesitate, as if the universe was holding its breath until someone forced it to pick a side. And when they tried, when they placed detectors at the slits to watch which path the photon took, the interference vanished. The stripes dissolved. Suddenly, those photons acted like marbles again, like they'd been waiting for permission to choose. As if the universe had whispered, "If you ask me to reveal the path, I will. But if you don't ask, it'll wander in every direction at once." This isn't some abstract thought experiment, it's a window into the heart of how things really work. Observation isn't just watching, it's participating. It's not about human consciousness staring in wonder. It's about any interaction that forces the system to stop being a ghost and start being a thing. Measure it, and the quantum mist clears. Leave it alone, and it spreads like smoke. Now, let's step back a moment and imagine you're in a lab in 1922, watching Otto Stern and Walter Gerlach do something even stranger. They send a beam of silver atoms through a magnetic field, expecting a smooth, blurry smear like throwing a handful of sand and watching it settle in a cloud. Instead, the beam splits cleanly in two. No blur, no gradient. Just two sharp spots, as if the atoms had somehow chosen between two paths before they even reached the screen. This wasn't a mistake. This was the discovery that one of nature's most fundamental property spin wasn't a smooth spectrum of possibilities. It was quantized. Like a coin that never lands on its side. Like a light switch that can't flicker halfway between on and off. The quantum world doesn't let you play in the middle. It's all or nothing. And if that doesn't make your head spin, try this in the everyday world. You can measure anything with infinite precision. But in the quantum world, some things come in fixed chunks. You can have a quarter of an electron. You can't have a half spin. It's like the universe handed you a deck of cards, but told you to only play with the aces and kings. Nothing in between. Now, put all these pieces together, Planck's quanta, Einstein's photons, Bohr's atom, and what do you get? A world where particles don't just exist in one place. They linger in many at once, where properties aren't smooth but jump from one possibility to another, where the act of looking doesn't just reveal the truth, it creates it. This wasn't comfortable news for the physicists of the early 1900s. Imagine you've spent your life believing physics is a neat, orderly book, only to open it and find that the chapters rearrange themselves depending on who's reading. Some, like Niels Bohr, said we should stop asking what particles are when we're not looking and just focus on what happens when we measure them. Others, like Einstein, refused to accept it. God does not play dice, he famously said, insisting there had to be some deeper, hidden reality waiting to be uncovered, and the debates raged sharp, passionate, and still echoing today. But here's the thing, the lab results didn't care about their arguments. Every time they ran the double-slit experiment, the interference pattern appeared when no one was watching. Every time they tried to peek at which path the photon took, the pattern vanished. Every time they sent silver atoms through a magnetic field, the beam split into two spots. The universe wasn't debating, it was behaving. And it was behaving in ways that forced physicists and, eventually, all of us to ask a radical question: what is reality? If it changes when we look. So let's pause here and breathe. Because this isn't just about science. It's about how we see. Imagine a coin spinning in the air, caught between possibilities. It's not just that we don't know which side it will land on. It's that, for a moment, it isn't heads or tails at all. It's both. Now imagine a violin string vibrating with every possible note at once, but only producing one when you pluck it. These aren't perfect metaphors, but they're close enough to give you a feel for the quantum world. It's not that it's weird. It's that it's delicate. Like frost on a window that melts when you breathe on it. Like a dream that dissolves the second you wake up. The quantum world reveals itself only when we're gentle. The moment we press too hard, it slips away, leaving us with the solid, predictable world we've built on top of it. That's why quantum computers are so fragile. Why experiments have to be set up just right. Why the universe, at our scale, feels so real. Now, let's step into the room where it all comes together. You're walking into a space filled with mist, thick in some corners, thin in others. If I asked you where a marble might be hiding in that fog, you couldn't point to a single spot. But you could look at the mist and say, it's more likely here, less likely there. That mist, that's the wave function. When scientists first tried to make sense of atoms, Bohr's model gave them a starting point: electrons orbiting in fixed steps. But they needed more. They needed a way to describe how electrons behave, not just as particles, not just as waves, but as something in between, something shimmering. Enter Erwin Schrödinger in 1926 with his equation. If Newton's laws are recipes for predicting how an apple falls, Schrödinger's equation is a recipe for predicting probabilities. It doesn't tell you where the electron is. It tells you where you're likely to find it. Instead of a sharp point, it paints a cloud or haze of possibilities. Scientists write it with the Greek letter psi. But let's call it the probability mist. The thicker the mist in a region, the higher the chance the electron will appear there when you look. Now, take that idea and apply it to the simplest atom of all, hydrogen. 1 proton, 1 electron. If you plug the numbers into Schrödinger's equation, you don't get neat circles like planets. You get shapes, delicate patterns of probability that physicists call orbitals. Imagine dropping a marble into a bowl of jelly that's vibrating. The ripples settle into standing waves, swells and quiet spots. Hydrogen orbitals are like that, but instead of jelly, they're made of probability itself. Some orbitals are spherical, like tiny soap bubbles around the nucleus. Others have lobes, like petals on a flower. The electron isn't buzzing around like a little moon. It's spread out, smeared into a standing wave of chance. Now, here's where it gets unsettling. If you ask, but where is the electron really? Quantum physics answers nowhere in particular until you measure it. Before that, it's living in its wave function, a state of possibility. The mist fills the room, waiting. And only when you look does the marble condense into one corner. That's why scientists say the wave function is the most complete description of a quantum system. It carries all the information about what could happen, but none about what will happen until you measure it. Think of it like a weather forecast. It might say there's a 60% chance of rain. That doesn't mean it's raining yet or that it won't. It just means the possibilities are weighed, and only when the day unfolds do you see the outcome. The wave function is like that, but for everything in the quantum world. Position, energy, spin, it holds the entire spread of potential futures. Now, here's the leap in the classical world. Uncertainty comes from our lack of knowledge. If you don't know where a coin fell under the couch, that's on you, not reality. But in the quantum world, uncertainty isn't ignorance. It's built into nature. The electron isn't hiding its address from you. It doesn't have an address until you look. That's why atoms are stable. Remember Bohr's energy steps. Schrödinger's equation deepened that picture. The electron's wave function forms standing patterns that can't collapse into nothing. These waves only exist in certain shapes like harmonics on a guitar string. The allowed orbitals are the notes the atom can play. And because of that, chemistry isn't just possible. It's rich. The colors of fireworks, the glow of a neon sign, the shape of the molecules in your body, all of it depends on these misty electron clouds. If electrons really orbited like planets, the world would be flat. But because they inhabit these strange, shimmering orbitals, atoms can bond in endless ways, weaving the complexity of life itself. Schrödinger himself was both amazed and tormented by his own equation. It worked too well. It predicted experiments with eerie accuracy. But what did it mean? Was the wave function a real, physical mist surrounding the nucleus? Or was it just a mathematical tool, a story we tell to make sense of outcomes? Some physicists say it's the most real thing we can talk about. Others say it's just a way to encode our knowledge. But here's the beauty: you don't have to choose. You can imagine it as a gentle haze, thicker here, thinner there. A reminder that not everything needs to be sharply defined to be meaningful. Sometimes the blur, the openness of possibility is what makes the world stable and alive. So close your eyes for a moment and picture this: a quiet hydrogen atom. 1 proton at the center. An electrons cloud shimmering softly around it. No rushing planets. No sudden collapses. Just a standing mist of chance, humming gently in the dark. And if that doesn't leave you feeling a little lighter, a little more curious about the world, then maybe you weren't listening closely enough. Because this isn't just about particles and equations. It's about seeing. And once you see it this way, you'll never look at reality the same again. Close your eyes for a moment and imagine standing at the edge of a great, shimmering mystery. Not the kind of mystery that frustrates you with its gaps, but the kind that thrives in the space between what we know and what we can only sense. This is the quantum world, the realm where certainty crumbles like sand slipping through fingers, only to reveal something far more extraordinary beneath. In the classical world, uncertainty was just a shadow of ignorance. If you couldn't see where that coin fell under the couch, it wasn't because the coin itself was uncertain. It was because your your knowledge hadn't caught her up. But here, uncertainty is the very fabric of things. The electron isn't playing hide and seek with us. It isn't waiting to be discovered, hiding behind some unseen curtain of information. No, the electron doesn't have a position at all, not until the moment you look. Not until the mist of possibility condenses into something solid in your hands. And that, my friend, is where the magic begins. Because if you've ever wondered why atoms don't dissolve into nothingness, why the world around you holds together at all, the answer lies in that very uncertainty. Picture this: electrons, errant planets zooming in perfect orbits. Their waves, standing still like the notes on a guitar string, vibrating in patterns that can't be squeezed or collapsed too tightly. Their harmonies trapped in the shape of the atom, each one humming with possibility until something disturbs the peace. Now take a deep breath and let your mind drift to a quiet forest at night, where a lantern cuts through the fog. The light doesn't just reveal what's already there, it creates what you can see. The fog itself is the wave function, a gentle haze of probabilities, thicker in some places, thinner in others. And when the lantern shines, when you reach out to touch it, the mist doesn't vanish, it chooses. One path solidifies, one possibility becomes real. The colors in your world, the glow of a neon sign, the shape of the molecules in your body, all of it depends on those shimmering electron clouds. Those standing waves of chance. Without this blur, without this dance between here and there, chemistry would be dull. Atoms would cling to each other like magnets stuck in place. And life as we know it would never have woven its tapestry. Schrödinger's equation gave us the map to this strange landscape, and it worked with a precision that bordered on the uncanny. But here's the question that has haunted physicists ever since: is the wave function real? Is it a physical mist? A shimmering cloud wrapped around the nucleus? Or is it just a story we tell ourselves to make sense of what we see? Some say it's the most real thing in the universe. Others argue it's merely the language of our understanding, a tool to predict without claiming to explain. And perhaps the beauty of it is that you don't have to choose. You can hold both ideas in your mind like two sides of the same coin. Spinning in the air, the mist is real, the certainty is real, and in the space between, the universe hums with quiet harmony. Let yourself sink into that thought for a moment. Imagine a single hydrogen atom, its proton at the center and that electron cloud swirling around it, not in circles, but in standing waves, like ripples frozen in time. No collapse, no sudden plunge into reality, just a soft, shimmering mist of possibility, humming in the dark. And in that hum, there's order, there's pattern, there's the promise that even in the smallest things, the universe speaks in rhythms we can almost hear if we listen closely enough. It's like watching a coin spin on a table. For a heartbeat, it's neither heads nor tails. It's a blur of both, suspended in time, and then Klinkone outcome becomes real. In the quantum world, that moment of choice isn't just about observation. It's about participation. When you measure, when you reach into the mist, you're not just revealing what was already there. You're shaping it. Now, let's step into Schrödinger's thought experiment, not because it's real, but because it's a doorway, a cat in a box, tied to the fate of a single radioactive atom. If the atom decays, the cat is dead. If it doesn't, the cat lives. But until you open the box, quantum mechanics says the cat is both, alive and dead, suspended in that strange superposition of possibilities. Of course, No real cat was ever harmed. Schrödinger wasn't cruel. He was trying to show us the tension between the tiny and the vast. Atoms play by the rules of the mist. Cats? Cats are solid. They're here or there, not both. So where does the transition happen? When does the blur of probability give way to the certainty of the everyday? Some say it's when the system touches the outside world, when it becomes entangled with something big enough to force a choice. Others say it's when we choose to look, when our act of asking pulls one reality from the many. The truth. It's still a debate. But what matters is the image it leaves us with the mist collapsing into one outcome when pressed, like a breath held too long before finally being released. Let's bring it closer to home. Imagine baking bread. While it's in the oven, it could be perfectly risen, slightly underdone, or even a little burnt. All possibilities exist in your mind. But the moment you open the door, the uncertainty collapses. One loaf becomes real. Was it always that way? In our world? Yes, but in the quantum world, before you peek, the bread really is all those things at once. Only when you look does it choose. That's the power of measurement, not just revealing, but creating reality in that instant. And here's the irony: our world feels solid because we're constantly measuring it. Light bounces off a chair, collapsing its position into something definite for your eyes to see. Air brushes against your skin, collapsing the warmth you feel into one stable value. The universe is in a constant act of becoming, of choosing, long before our minds take notice. Schrödinger's cat may haunt our imaginations, but it's not just a riddle. It's a reminder that reality is deeper, stranger, and far more alive than we ever imagined. In one interpretation, the cat is both alive and dead until we look. In another, the universe splits into parallel realities, one where the cat lives and one where it doesn't. In still others, the wave function never collapses at all, it's just our understanding that changes. But here's the truth that ties them all together: outcomes don't exist until something forces them to. The act of looking isn't passive. It's part of the story. It's part of the fabric of reality itself. Think of it like a lantern in the fog. Before the light, the mist spreads without shape. When the beam shines, it carves a path through the darkness, defining what you can see. The lantern is measurement. The fog is the wave function. And the clear path is the reality you're left with. This way of seeing brings a kind of humility. It tells us that the world isn't a finished painting, waiting quietly with all its details in place. It's a living thing, pliable, flexibly a realm of may that solidifies only when touched. Far from making reality less real, this makes it more alive, always in the act of becoming. So as you sit here, listening, let your mind wander to that spinning coin. Neither heads nor tails until you glance to a cat in a box, safe and unsafe in the same breath, to a loaf of bread, both risen and fallen, waiting for your hand to open the oven door. These aren't puzzles to frustrate you. They're invitations to wonder. And if your eyes grow heavy now, let them close. After all, collapse isn't just for electrons. It's for thoughts, too, which fade into one dream as you drift to sleep. Now, think of something familiar. You're driving, and you know exactly where the car is on the road. You glance at the speedometer, and you know how fast it's moving. You toss a ball to a friend, and you can trace its arc with confidence, knowing where it will land. In the classical world, this combination of position and momentum feels natural, almost obvious. But in the quantum world, even that certainty dissolves. Werner Heisenberg uncovered this in 1927 with his uncertainty principle. You cannot know both where something is and how fast it's moving with perfect precision. The sharper you make one, the blurrier the other becomes. It's not about faulty instruments or poor eyesight. It's woven into the structure of nature itself. Imagine trying to photograph a hummingbird in flight. If you use a fast shutter speed, you freeze its wings in place. But you lose the blur of motion, the rhythm of its beating. If you slow it down, you capture the wings' dance, but the exact position of each feather slips away. The quantum world doesn't give you both. The universe insists on a trade-off. A tightly confined electron squeezed into a tiny space must have wildly uncertain momentum. It would dart away with tremendous energy rather than stay. So instead, it hovers, balanced by the very uncertainty that keeps it alive. The mist doesn't just surround the atom, it holds it together. And here's the gift of this strangeness: it's why atoms don't collapse into nothing. If electrons were tiny marbles circling a nucleus, they'd spiral inward and vanish. But the uncertainty principle prevents that. To force an electron into a small space would demand impossible precision in its speed. Instead, it exists as a cloud, a shimmering balance between here and there, held steady by the very rules that make the universe possible. In that mist, there's stability, there's harmony, there's the quiet rhythm of existence itself. And as you sit here, breathing, remember this: the world isn't just out there, waiting to be discovered. It's here, waiting to be chosen, one possibility at a time. Close your eyes for just a moment, and let me guide you through the quietest revolution of all time, and not in machines or markets, but in how the world is. You're already familiar with the rhythms of certainty, a car's steady hum on the road, the confident arc of a thrown ball landing in your friend's waiting hands. In that world, you can know both where something is and how fast it moves. But step closer now, where the air itself seems to whisper in probabilities, and you'll find the universe doesn't play by those rules. Here, at the edges of what you can touch or see, reality softens like the focus of a camera lens. The sharper you try to make one truth the exact place of a feather on a hummingbird's wing, the blurrier the other becomes. This isn't a flaw in your vision or your tools. It's the universe's quiet way of saying some things are not yours to know all at once. Werner Heisenberg, one of the first to unravel this truth, called it the uncertainty principle. And though the word uncertainty might make you think of doubt, this isn't about ignorance. It's about the very fabric of existence refusing to be pinned down. Atoms, electrons, photons, they don't behave like tiny marbles rolling on a table. They behave like waves, like mist, like possibilities stretched thin across the void. Try to squeeze one too tightly to force it into a single place, and its speed becomes a wild, untamed thing. Loosen your grip, and its location fades into a gentle cloud. This isn't chaos, it's balance. It's the reason the world doesn't collapse in on itself. Imagine a cat, restless in a box. The smaller the box, the more it thrashes, the more energy it has to escape. Give it room, and it settles. Atoms do the same. Electrons don't spiral into their nuclei, because the universe won't let them. The very act of confining them makes their motion unpredictable, their energy boundless. Stability is born from this softness, this refusal to be certain. Picture music now, not a single note, but the space between them. A tuning fork struck once holds a perfect pitch, but no rhythm. A drum beat is precise in time, but it hums with many frequencies at once. You can't have both sharp and smooth in the same sound. The universe does the same with position and motion. It's a trade-off written into the rules of the game. And if that feels unsettling, let it. Uncertainty isn't the absence of answers. It's the presence of something deeper, the idea that reality isn't a rigid map, but a living, breathing thing. Always adjusting, always in motion. Now, take a step further and let your mind stretch beyond what's certain. In the world, you know, a light switch either on or off. A coin either heads or tails, there's no in between. But down here, where the air hums with unseen forces, particles don't choose, they are. An electron isn't here or there. It's both at once, until something your gaze, a measurement, a single breath of air collapses it into one. This isn't magic, it's superposition. The universe's way of holding all possibilities gently, like a hand cupping dew. Flip a coin in your mind, and before it lands, it's both sides at the same time. Walk down a road, and until you turn, you're at every fork. Drink from a glass, and until you sip, the water is both full and empty. It sounds like a dream, and perhaps it is, but dreams too. are made of this same stuff. Before the morning light chooses which parts to remember, your mind drifts through layered stories, shimmering with every possible ending. Why does nature behave this way? Because particles aren't solid things, they're waves, and waves overlap. Two ripples in water pass through each other, merging and separating as if nothing happened. That's what superposition is, the mathematics of overlap, written into the deepest layers of the world. And though it feels fragile like a soap bubble about to pop, it's not just a curiosity. It's the foundation of something new. Quantum computers, for instance, don't just calculate one path at a time. They explore all of them at once. While a classical computer walks through a maze, testing each corridor, a quantum one drifts through them all like mist, sensing where the exit lies before collapsing into the answer. It's not about speed. It's about possibility. The universe doesn't rush to decide. It holds options like a symphony tuning before the first note, each instrument playing every possible melody until the conductor's hand chooses one. So let yourself rest now, and imagine the world this way, not as a hard grid of certainties, but as a watercolor painting where edges blur into one another. The orchestra tuning in the half-light, each note a possibility not yet played. The card deck in your hands, every face visible at once. The road splitting before you, both paths walked until you look back. These aren't puzzles to solve. They're lullabies of chance. The universe humming in layered harmonies before settling into a single song. And if your eyes close, know this: your dreams, too, are superposition stories shimmering with every possible ending until morning chooses which to keep. The next time you feel the weight of uncertainty, remember this: it's not a lack of answers. It's the universe giving itself room to be. And in that space, there's no collapse, only creation. Close your eyes for a moment and imagine holding two delicate glass marbles, each one humming with the faintest vibration of unseen energy. Now picture yourself rolling one marble across a table, while your friend does the same with theirs. Miles away, in our everyday world, their movements are entirely separate. One marble spins here, the other spins there, their fates unrelated. But now imagine this: no matter how far apart they roll, the moment you catch one marble and see it land on a certain side, your friend's marble instantly mirrors that choice, as if guided by a silent thread. That, my friend, is entanglement, the universe's way of stitching together distant realities with threads of pure possibility. This isn't just some abstract trick of physics, it's the very fabric of how quantum systems communicate. When two particles become entangled, they don't just share information. They become a single, unified system. No matter the distance, measure one, and the other knows the answer before you even look. Einstein called this spooky action at a distance, and for decades, scientists and philosophers grappled with how such instant connections could exist without violating the speed of light. But experiments have shown time and again that this isn't magic, it's physics. It's the universe whispering that separation is an illusion when you're speaking the language of quantum mechanics. Let's make it even stranger. Picture two dancers, blindfolded, standing on opposite sides of a vast, empty stage. They've never seen each other, never practiced together. Yet, when one lifts a hand, the other lifts theirs in perfect, instantaneous harmony. No signal passes between them. No conductor gives the cue. They simply are one movement, two bodies moving as if connected by an invisible thread. That's entanglement in living form, a bond that defies the very idea of distance. And here's the mind-bending part: you can't even describe one dancer without describing the other. Their identities are intertwined. Measure the left hand of one, and the right hand of the other instantly reflects that choice, as if the entire system had already decided. This isn't just a parlor trick of nature, it's the cornerstone of what makes quantum technology possible. When you build a quantum computer, you're not just flipping bits like a classical machine. You're weaving together entangled particles, each one a note in a symphony of possibility, A single entangled pair can encode far more information than two separate classical bits ever could. Need to solve a complex problem. Instead of walking one path at a time, a quantum system can explore all paths simultaneously, thanks to entanglement's ability to link outcomes across vast distances. It's as if you're holding a map where every road is lit up at once, and the moment you choose one, the rest fade into the background, but not before revealing their secrets. Now, let's bring this back to your own life. Entanglement reminds us that the universe doesn't work in isolated snapshots. Every choice, every action, doesn't just ripple outward, it connects. Think of the last time you made a decision that felt impossible to reverse. Maybe it was a conversation you didn't expect to have, an opportunity that appeared out of nowhere, or a synchronicity that left you wondering if the universe was nudging you. Entanglement suggests that these moments aren't random. They're echoes of a deeper, unseen harmony, where distant events are linked in ways we can't always see. But here's the beautiful truth: this isn't just about particles or computers. It's about you. You, too, are part of a vast, entangled web. The thoughts you have now might be subtly connected to choices made years ago, just as your next step could ripple forward in ways you can't yet imagine. The fragility of quantum states show easily they collapse when observed mirrors how our own possibilities shift the moment we focus on them. One glance, one decision, and a world of what-ifs narrows into a single path. So rest for a moment and imagine this: you're standing at a crossroads, and the universe is offering you two paths. In the classical world, you'd have to choose one and walk it alone. But in the quantum world, you're entangled with every possible version of yourself. Every choice you make doesn't just lead to one outcome, it holds the seeds of many. And the strangest part, the moment you step forward, the other paths don't vanish. They simply wait, patient and unseen, until another version of you chooses them. This is how superposition and entanglement work in concert. One gives you the possibility of many futures, and the other binds them together in a way that feels almost alive. It's as if the universe is humming a melody you've never heard before, a song where every note is both itself and its opposite, where distance means nothing, and where the very act of listening changes the tune. So when you feel the weight of a decision, remember this: you're not just standing at a fork in the road. You're standing in a vast, shimmering labyrinth where every corridor is alive with possibility. And the beauty: you don't have to rush. The universe doesn't either. It waits, holding all the answers, until you're ready to step forward. And when you do, the paths behind you will fade, but they'll never truly be gone. Because in the quantum world, nothing is ever truly lost. It's all still out there, waiting, entangled, and ready to unfold when the time is right. Close your eyes for a moment and breathe deeply. Because what I'm about to share isn't just a story about particles, it's a story about connection, about unseen threads that bind what we think of as separate, and about the quiet revolution happening at the edges of science and wonder. You see, there's a law in our ordinary world that feels like common sense. If you throw a ball up a hill, it won't just teleport to the other side unless you give it enough energy to climb over. That's the way things work. But in the quantum world, the rules are different. They're fluid. They're alive. Imagine this: a particle isn't just a single point with one path, like a coin spinning toward heads or tails. It's a mist, a swirling cloud of possibilities, where every outcome hums with equal weight until something disturbs it. And here's the astonishing part: that mist doesn't vanish when it hits a barrier. It doesn't stop. It doesn't obey the rules we've written for the world we see. Instead, it seeps, like fog curling around a mountain or light spilling softly through the edges of a curtain. Most of it bounces back, but a whisper of it lingers. A delicate thread reaches just beyond. And if the barrier is thin enough, if the mountain is low enough, there's a chance. Not a guarantee, but a chance that the particle will appear on the other side, as if it had never been blocked at all. This isn't magic, it's physics. It's called quantum tunneling, and it's one of the most counterintuitive yet deeply real phenomena in the universe. Think of it like this: you're standing in front of a locked door, and you don't have the key. In our everyday world, you'd have to find another way around or break it down. But in the quantum world, the particle doesn't need to climb over the obstacle. It doesn't even need to press against it. The mist of possibilities slips through the crack, and suddenly, you're on the other side without ever touching the barrier. It defies logic, but it happens all the time at the smallest scales. And here's why this matters, because it teaches us that the world isn't as rigid as we think. The boundaries we draw, the walls between here and there, between possible and impossible aren't absolute. They're more like the edges of a dream, where the rules bend just enough to let something unexpected slip through. This isn't just about particles anymore. It's about perspective. It's about seeing the world, not as a collection of separate things, but as a tapestry where the threads are woven together in ways we're only beginning to understand. Now, let's pull back a little further and ask if particles can slip through barriers that shouldn't allow them. What does that say about the nature of separation itself? In our daily lives, we accept that things are distinct. A cup is hot or cold. A door is open or shut. A path is here or there. But in the quantum realm, those divisions blur. Two particles can be entangled across light years, their fates linked in a way that transcends distance. One doesn't exist without the other. They are not two, but one shared story. And when you measure one, the other responds instantly, as if it had been waiting for that moment all along. Einstein called it spooky action at a distance, and he couldn't reconcile it with the universe he imagined where nothing instantaneously affects anything else, where the rules are local and neat. But the experiments don't lie. Decades of testing, of stretching detectors across miles, of randomizing settings at the last possible moment, have all led to the same conclusion: the connections are real. They're not hidden messages, they're not secret instructions. They're the fabric of reality itself, stitching together what we see as separate into something far more intimate. So let's sit with this for a moment. Imagine two dancers on opposite sides of a vast stage, blindfolded, unable to hear each other. Yet when one lifts an arm, the other lifts the same arm in perfect synchrony. No signal is sent, no cue is given. They simply move as one, bound by a connection that defies the space between them. That is entanglement. And it's not just a curiosity of physics, it's a metaphor for something deeper. Think about the times in your life when you felt unseen threads pulling you forward. Moments when a decision made here seemed to echo in possibilities over there, as if the universe had been whispering to you all along. Maybe it's the way a conversation with a stranger led to an unexpected opportunity, or how a small act of kindness rippled outward in ways you couldn't have predicted. These aren't coincidences. They're glimpses of the same principle at work: that separation is not always as absolute as it seems. That beneath the surface of the ordinary, there are currents of connection waiting to be recognized. And here's the beautiful part: you don't have to understand the math behind entanglement to feel its truth. You just have to trust that the world is stranger and more generous than it appears. That the barriers you see aren't always barriers at all. That the possibilities you've dismissed might still be lingering just beyond reach, waiting for the right mist of intention to carry them through. So take a deep breath and let yourself imagine this: two sparks of light, born from the same flame, drifting apart across the vastness of space. No matter how far they go, they remain linked. Their fates are written not as individuals, but as one. That's entanglement. And it's a reminder that, in some hidden way, we're all part of that same shared wave function too. Now, let's bring this closer to home. Suppose you're standing at a crossroads, unsure which path to take. In the everyday world, you'd weigh the pros and cons, map out the risks, and choose the one that feels most certain. But what if the quantum world has something to teach us here? What if the answer isn't just one path, but a mist of possibility, some of them leading to dead ends, others seeping through unexpected cracks to places you never imagined? You don't have to force your way over every obstacle. Sometimes, the right path isn't the one that's most obvious. It's the one that slips through the barrier when you least expect it. It's the connection you didn't see coming. It's the entangled possibility that waits on the other side, patient and unseen, until you're ready to step forward. And here's the courageous truth: you don't have to wait for certainty to move. The mist doesn't need a map. It doesn't need permission. It just needs space to unfold. So when you're faced with a choice that feels impossible, ask yourself, what if the answer isn't over the hill, but through the fog? What if the path you're searching for is already here, waiting for you to recognize the connection? Entanglement isn't just about particles anymore. It's about trust. It's about believing that the world is more interconnected than it seems, that the threads of your life are woven into something far greater than you can see. So take a moment to quiet your mind and imagine, where in your life do you feel separated? Where do you sense the weight of barriers, internal or external, that seem impossible to cross? What if those barriers aren't as solid as they appear? What if, like the quantum mist, they're just edges waiting to be seeped through? What if the answer isn't to climb over, but to trust that the connection is already there? You are not alone in this. The universe is not a collection of isolated points, but a tapestry of entangled possibilities. And you are part of that tapestry. Your choices, your doubts, your dreams, they are all threads in a story that's far bigger than you can imagine. So breathe, and when you're ready, take that first step, not toward certainty, but toward connection. Not over the hill, but through the mist. Because the other side isn't just a place you'll reach, it's a place you're already part of. You just have to trust the thread. Close your eyes for a moment and imagine this: you are standing at the edge of the universe, gazing into the vastness of space where nothing seems to be there at all. No stars, no planets, just endless darkness stretching in every direction. This is how we often picture empty spaces, still, silent, and devoid of anything. But what if I told you that what we call empty is anything but that? Beneath that quiet darkness, there is a symphony of unseen forces, a hum of energy so subtle it defies our everyday understanding. The universe doesn't just whisper, it breathes, and even in its most silent corners, it is alive with possibility. Now, let's bring this idea closer to home. Imagine walking into a room that looks completely empty: no furniture, no movement, just bare walls and a sense of stillness. You stand there, waiting for silence. But then you hear it: the faint buzz of a refrigerator, the creak of pipes settling, the whisper of air slipping through unseen cracks. It's not truly silent. There's always something there, even when it seems like nothing. That's the nature of space at its most fundamental level. The empty void between stars, the silence of the cosmos. It's not a void at all. It's a restless sea of energy, a place where particles flicker in and out of existence like stars in a night sky that only quantum eyes can see. Scientists call this the vacuum fluctuations, the constant, tiny disturbances in the fabric of reality itself. For just a fraction of a second, particles pop into being, only to vanish again, borrowing energy from the very fabric of space. It sounds like magic, but it's science. And it's everywhere, everywhere you look. Even in the most empty corners of the universe, this hidden dance is taking place. It's as if the universe itself is never truly still. It's always humming, always shifting, always creating and uncreating in ways we can barely comprehend. There's a beautiful experiment that proves this. Take two uncharged metal plates and place them very close together in what should be an empty vacuum. According to the rules we've always known, nothing should happen. But in the quantum world, something does. The plates are gently pulled together, as though an invisible hand is guiding them. This is the Casimir effect, a reminder that even emptiness has weight, has energy, has force. It's the universe showing us that nothing is ever as simple as it seems. The silence you think you hear is never truly silent. The stillness you feel is never truly still. Now, let's think about what this means for you. For me, for all of us. We live in a world that often feels divided, people separated by distance, by doubt, by the weight of unseen barriers. We look at challenges ahead and sometimes they seem impossible, like hills too steep to climb or doors too locked to open. But what if those barriers aren't as absolute as they appear? What if, even in the places where we feel stuck, there is still movement, still possibility, still the flicker of something new being born? Consider this in the quantum world. Particles don't just exist in one place or another. They exist in a mist of probabilities, a cloud of potential that stretches beyond what we can see. A ball rolling down a hill doesn't always obey the rules we expect. Sometimes, it just appears on the other side, as if the hill itself had briefly become transparent. That's tunneling, a reminder that even the most impossible seeming obstacles aren't always final. There's always a chance, no matter how small, that you'll find yourself on the other side of doubt, of fear, of whatever is holding you back. The sun overhead is burning because of this same principle. Deep in its core, particles are colliding in ways that defy classical physics. They should never meet. Yet they do, because they tunnel through the barriers that should keep them apart. Every sunrise is a testament to the fact that the universe doesn't always follow the rules we think it should. It bends, it surprises, it allows for miracles where we least expect them. So, as you stand at the edge of your own challenges, remember this: the space around you isn't empty. It's alive with possibility. The doors that seem locked might just be waiting for a flicker of chance to open. The hills that look insurmountable might have a way through you haven't seen yet. The universe is stranger, more connected, and far more generous than we often realize. And if it can allow particles to slip through barriers and create stars from nothingness, then perhaps it can help you. 2. Find your way through. Take a deep breath. The world is not as divided as it seems. The barriers you face are not as impenetrable as they feel. And even in the quietest moments, the universe is humming, reminding you that you are never truly alone. Never truly without support. Never truly without a path forward. So trust in the flicker of possibility. Trust in the unseen threads that connect you to everything else. And believe, just for a moment, that even the most impossible dreams might just be waiting for their chance to shine. Imagine standing in a room that feels utterly still, the kind of quiet that makes you pause and listen. At first, all you hear is silence, deep, unbroken, and heavy with stillness. Then, just barely, a whisper reaches you. The hum of a refrigerator in the next room. The faint creak of pipes settling into place. The soft sigh of air slipping through cracks you never noticed before. It isn't truly empty, this silence. Not even close. And neither is the space around us. What we call empty is never truly empty. The universe holds secrets in its quietest corners. Take the Casimir effect, named for a Dutch physicist who uncovered something astonishing. Place 2 uncharged metal plates, just a whisper apart, in what we think of as a perfect vacuum. Classical physics says nothing should happen, no force, no movement, just stillness. But reality surprises us. The plates are drawn together, as though an invisible hand were gently pressing them closer. There's no physical contact, no energy added, and yet they move. The force comes from the very fabric of the vacuum itself. A restless mist of quantum possibilities swirling just beneath our notice. Between the plates, the fluctuations of this hidden energy shift ever so slightly, creating an imbalance that nudges them inward. It's tiny, almost imperceptible, but it's there, proof that emptiness is never as simple as it seems. Think of it like the pause in music between notes. Even in that silence, there's tension. A breath held before the next sound. The vacuum is that pause, alive with potential vibrations. The plates feel the pull of those silent moments, a reminder that what looks still may be the most alive of all. This hidden energy doesn't just play tricks in a lab. It's woven into the very expansion of the universe. Astronomers have discovered that galaxies aren't just drifting apart, they're accelerating, as if some unseen force is pushing them farther and faster with every passing moment. This mysterious energy, called dark energy, is thought to be the restless vacuum itself, stretched across the cosmos like an invisible ocean. Quantum theory suggests this vacuum carries more energy than we can see. Yet it remains subtle, hiding in plain sight. How can something be both wildly energetic and so quiet? The answer is one of science's greatest unsolved puzzles, a whisper waiting to be heard. Closer to home, this restless energy shapes the very particles around us. In quantum field theory, every particle is a ripple in an underlying field that fills all of space. The vacuum isn't the absence of these fields, it's their lowest energy state, still flickering with fluctuations. Picture a pond on the calmest day. The surface appears still, but tiny ripples dance beneath. The vacuum is that pond, never fully flat. And these ripples aren't meaningless. They interact with particles, shaping their mass and charge as though each electron is never truly alone. It's as if every particle carries a shimmering crowd of ghostly companions, always present but never seen. So when you sit in a quiet forest at night, feeling the stillness press in around you, remember this, that silence isn't empty. Lean in closer, and you'll hear the rustle of leaves, the distant call of an owl, the movement of unseen creatures. The same is true in the quiet moments of your own life. A pause in conversation, a moment before sleep. Even the space between thoughts each holds hidden potential, waiting to stir. The Casimir effect is more than a scientific curiosity. It's a reminder that what looks empty may be the most alive of all. Two plates pressed together by invisible forces, just as you might feel the gentle pressure of possibilities even in stillness. The universe doesn't wait for permission to be full. It simply is. As you rest now, imagine the air around you humming faintly, not with noise but with quiet energy. The room isn't silent, it's alive with fluctuations too small to notice. Yet always there, the universe expands, carried by this hidden force. And so do you, shaped by it in ways you can't yet see. It's not frightening, it's comforting. Emptiness is never truly empty. And in that truth, there's peace. Now, let's step deeper into the strange, into a world where time itself seems to bend and whisper. Imagine an experiment so clever it makes reality itself feel like a story being written backward. In the double-slit experiment, a single photon particle of light passes through two slits and creates a pattern of interference, as if it's split into waves and recombined. But add a detector to watch which slit it takes, and suddenly, the interference disappears. The photon behaves like a particle, choosing one path or the other. The order seems clear, the photon travels, then we measure it. But what if the choice of how to measure happens after the photon has already passed through the slits? Physicist John Wheeler asked this daring question in 1978. Suppose the photon moves through the experiment, and only later do we decide whether to observe its path or not. In classical logic, the photon's behavior should already be set by the time it reaches the slits. Yet experiments inspired by Wheeler's idea suggest something stranger. The photon acts as though it somehow knew in advance whether it would be measured as a wave or a particle. Nothing supernatural happens, of course. What these experiments reveal is that in quantum mechanics, outcomes aren't determined until the moment of measurement. The very act of deciding how to look shapes what we see. The quantum eraser takes this even further. Here, information about the photon's path is created but can later be erased. If the information exists, even if no one looks at it, the interference pattern vanishes and the photon behaves like a particle. But if that information is erased, the pattern returns. as if the photon's wave-like nature is restored. Reality seems to ask, is this information knowable? If yes, the photon chooses a path. If no, it behaves as a wave. It's as if the universe cares less about what happened and more about what can be known. Let me tell you a story to soften this idea. Imagine writing in a diary, each entry a record of your day. Now, suppose you burn the diary before anyone reads it. Did those details ever truly exist in a meaningful way? In quantum physics, the answer would be no. If the information cannot, in principle, be known, then it's as if it never happened at all. The photon's behavior shifts because the rules of the game have changed. Knowledge its erasure shapes reality. This isn't magic. It's a reminder that in the quantum world, cause and effect aren't simple arrows. First, the photon moves. Then, we decide how to measure it. But in between, the story isn't fully written. The past isn't locked in until the future arrives. It's as if the universe leaves things open, waiting for the full picture to emerge. Think of it like a play where the final act is written last, once it's in place. The earlier acts seem to have been leading toward it all along. Or imagine footprints in the sand that appear different depending on whether you shine a light on them later. The events are flexible until observed in full context. These experiments don't rewrite history, they reveal that quantum events aren't fully decided until all the interactions, including possible measurements, are complete. The past is pliable until the future settles it. So as you drift deeper into rest, imagine a diary written in invisible ink. Its words fade or reappear depending on whether you keep it or let it burn. Imagine photons at the slits, their paths undecided until you choose the lens through which to see them. Imagine the universe itself holding open possibilities, patient and unhurried, waiting for you to decide. By the 1920s, quantum mechanics had grown from a few curious puzzles into a full-fledged theory, one that could predict the behavior of atoms, light, and matter with breathtaking precision. Yet, at its heart, there was still a gnawing question: what does it all mean? How do we understand a world where particles exist as probabilities until measured? The answer came from a quiet institute in Copenhagen, where Niels Bohr and his colleagues debated late into the night. Bohr's solution was both radical and practical. He argued that we should stop asking what a particle really is before it's measured. The wave functioner cloud of probability shouldn't be thought of as a literal thing, but as a tool for predicting outcomes. Reality, Bohr said, isn't defined until it's observed. The act of measurement is what turns potential into actuality. Imagine a book with blank pages. As long as it's closed, the words aren't written. Only when you open it and begin to read do the sentences appear. In Bohr's view, the universe is like that book. The wave function holds all possible stories, and measurement is the moment when one is chosen and written into reality. This was a shocking idea. For centuries, science had assumed that objects have definite properties whether or not we look, but quantum mechanics shattered that certainty. For centuries, we've believed that the world exists independently of our perception, that the sun shines even when no one watches, that the moon orbits the Earth whether we notice or not. Quantum mechanics doesn't say we're wrong. It says we're incomplete. The universe doesn't wait for our attention to begin, but it also doesn't finish its story until we're part of it. So when you close your eyes tonight, remember this: the quiet moments aren't empty. They're full of possibilities, waiting to be measured, to be chosen, to become real. The vacuum hums with energy. Photons whisper at the slits, their paths undecided. And in the space between what is and what will be, there's room for everything to shift. You are part of that story. The universe leaves the past open until the future arrives. And in that space, anything is possible. Picture this: you're walking along a shoreline at dusk, the tide pulling in and out in slow, deliberate waves. The sand beneath your feet is soft and shifting, each grain holding its own story, yet the whole beach is a moving, uncertain landscape. Now imagine that every step you take isn't just pressing into the sand, but choosing it into being. Until that moment, the grains could have been anywhere. Suspended in the possibility of the tide. That's the quantum world in a nutshell, where everything is fluid. Everything is waiting. Not because it's broken, but because it's alive with potential. And you're the one who gets to step on it. This isn't abstract philosophy, it's how the universe works at its most fundamental level. Think of it like a diary written in invisible ink. The pages are blank, the words unreadable until you decide to open it. The ink might fade if you close it again, but the potential was always there, just waiting for you to turn the page. That's the wave function in action, a cloud of possibilities, a mist of what could be, until something, an observation, a choice, a glance collapses it into one reality. And here's the beautiful part: the universe doesn't rush. It doesn't force the story to be written until it has to. Unfinished chapters, unanswered questions, even the weight of unresolved feelings. They're not failures. They're the sand waiting for your footsteps. Let's take a step back for a moment. By the 1920s, quantum mechanics wasn't just a curious puzzle anymore, it was a revolution. Physicists like Niels Bohr had turned these strange ideas into a powerful tool. One that could predict the behavior of atoms, light, and even the fabric of matter with eerie precision. But beneath all the math and the experiments, there was a deeper question burning. What does it all mean? How do we make sense of a world where particles don't have definite properties until we measure them? Where reality itself seems to hinge on observation? Bohr's answer was radical. He said, in essence, stop asking. Not because the questions don't matter, but because the answers might be beyond use, at least for now. Imagine a book lying closed on a table. The pages are blank, the story unwritten. Only when you open it do the words appear, one by one. That's Bohr's universe. The wave function is the closed book. The could be of everything, and measurement is the act of opening it. The moment you turn the page, the story is chosen. The particle takes its path. The cat is, the infamous Schrödinger's cat, is both alive and dead until you look. Not because the universe is cruel, but because the rules are different here. Reality isn't a fixed stage set, it's a script that stays flexible until the curtain rises. And let's be honest, this idea can feel unsettling. For centuries, science told us that objects have definite properties whether we're looking or not. A chair is solid even if no one's sitting on it. A star burns whether anyone's watching. Bohr wasn't denying that. He was pointing out that at the smallest scales, the rules change. Particles don't have fixed paths, positions, or energies until something in the world forces them to declare one. It's like saying, you can't ask a sentence what it is before it's written. The ink hasn't touched the page yet. Now, you might be thinking, that sounds too neat. There has to be more to it. And you'd be right. Not everyone was comfortable with Bohr's view. Albert Einstein, for one, pushed back fiercely. He believed reality should exist independently of our observations. The moon is there, he'd say, even if I'm not looking at it. For Einstein, Bohr's interpretation felt like giving up on the deeper truth of nature. But Bohr had a counter. Physics isn't about what nature is. It's about what we can say about nature. The wave function. Those probabilities we measure aren't shadows of some hidden reality. They are the reality we can talk about. It's like sailing. You might not see the currents beneath the waves, but you learn to trust the wind and the tide. Bohr's idea was the same: focus on what can be measured, what can be predicted, and don't worry too much about what lies unseen. So let's sit with that for a moment. Reality isn't always what we expect. It's not always firm beneath our feet. And in that uncertainty, there's a strange kind of freedom. The world isn't compelled to declare itself until it has to. It holds possibilities open, like a book waiting to be read, or a diary waiting for its pages to be filled. And that's not a flaw, that's how it's built. Now, you might be wondering if Bohr's view is the standard. Why do physicists still argue about it? Great question. Because science isn't about settling everything, it's about asking better questions. And over the years, other interpretations have emerged, each offering a different lens on the same strange reality. Think of them like different translations of the same poem. The words are the same, but the images they create can feel wildly different. Take the many worlds interpretation, for example, introduced in the 1950s by Hugh Everett. It's a breathtaking idea every time a quantum decision is made. The universe splits. You're standing at a crossroads, and instead of choosing one path, both paths are taken. In one universe, you walk left. In another, you walk right. Schrödinger's cat, not alive and dead in a fuzzy middle alive in one universe. Dead in another. The wave function never collapses. It just keeps branching, creating an endless tree of realities where every possible outcome exists somewhere. It's like a novel that keeps splitting into sequels each time a choice is made. The story divides, and every version is written. Some find this vision awe-inspiring. Others find it overwhelming. But here's the thing, it's just one way of imagining the quantum strangeness. And it tells us something profound. Every choice isn't just a single story. It's the beginning of many. Then there are objective collapse theories. In these models, the wave function collapses on its own, without needing an observer. It's like a soap bubble that can only stretch so far before popping into a single drop. Reality is constantly making choices in the background, whether we're looking or not. It's a firm, mechanical way of seeing the world. Randomness isn't just in our minds. It's built into nature itself, like dice being rolled behind a curtain. But so far, experiments haven't shown clear evidence of this collapse happening. The universe keeps its secrets close. And then there's cubism, quantum Bayesianism, which turns the idea of the wave function on its head. In this view, the wave function isn't a physical mist floating around particles. It's a tool for expressing your beliefs about what you might observe, just like a weather forecast reflects probabilities based on available data. Cubism says the wave function reflects your knowledge, not some objective state of nature. Imagine two hikers looking at the same mountain trail. One expects snow ahead. The other expects dry ground. Their forecasts are different, but the mountain is the same. Cubism suggests quantum states are like that, expressions of belief, not literal clouds of possibility. When you measure something, you're not collapsing the universe. You're updating your expectations, learning more about the terrain you're navigating. So which one is right? Many worlds with its infinite libraries of outcomes. Objective collapse with its quiet, mechanical choices. Cubism with its focus on personal knowledge. The truth is, no one knows. And that's the beauty of it. All of these interpretations make the same predictions when it comes to experiments. Quantum mechanics is democratic in that way different worldviews can coexist, each offering a slightly different way of holding the same strange reality. For you, though, the real takeaway isn't about picking a side. It's about seeing the flexibility in the world and in yourself. Imagine yourself reading a novel that splits into infinite sequels. Or picture a soap bubble that snaps into a single drop at the right moment. Or think of yourself checking the weather, updating your forecast as clouds shift. Each image is a different way of understanding the same quantum mystery. And perhaps, in all of this, there's a quiet lesson sometimes. Uncertainty isn't something to fear. It's something to trust. The world isn't always compelled to declare itself until it has to. And that openness, that's where the magic happens. So as you sit here now, take a deep breath. The past is written, those pages are turned, those choices are made. But the present is the quiet act of measurement, the pen pressing softly on the page, the step taken into the sand, and the future. The future is the diary waiting to be read, the book waiting to be opened, the wave function waiting to collapse into the story you're about to live. The universe has a way of leaving things unresolved until the right moment. And that's not a problem, it's an invitation. To trust the process, to embrace the uncertainty, To know that every step you take, every choice you make, isn't just writing your story, it's choosing the one you're ready to live. Now imagine stepping back from the quantum dance where cats hover between life and death and possibilities stretch like soap bubblesomely to find that beneath it all lies an even deeper quiet. The universe isn't just made of tiny balls bouncing like marbles in a cosmic game. No, it's woven from something far more fluid, far more alive. Picture this instead of a box of marbles. You're standing in an empty room. Not truly empty. Not at all. The walls aren't just walls, they're alive with invisible sheets, stretching infinitely in every direction. These are fields. Fields of light, fields of matter, fields of force, all humming quietly, weighting every particle you've ever known, every electron, every photon. Every quark is not a solid bead, but a ripple on the surface of one of these fields. Think of a pond on a still morning. The water lies flat, smooth, untouched. But drop a stone in, and concentric waves spread outward. The water wasn't broken before it was whole. The ripples aren't separate from the pond, they're the pond's way of moving, of expressing energy. Now replace the pond with the fabric of space itself. The electron isn't a tiny ball, it's a ripple in the electron field. The photon isn't a particle of light, it's a shiver in the electromagnetic field. Even the emptiest corner of the cosmos isn't empty. Fields fill it, fields that could ripple at any moment if the right energy stirs them. You, right now, are made of these ripples. Your body isn't a collection of solid parts, but a temporary dance of fields vibrating into being and fading away. This changes everything. Particles aren't permanent. They're like notes in a symphony, brief flashes of sound in the larger harmony. Crash two ripples together with enough force, and the energy reshapes the field. What was an electron might become a quark. What was light might dissolve into heat. It's not about breaking things apart, it's about rearranging the fabric of existence itself. The universe isn't a machine of gears and levers. It's a living canvas, where every stroke is a field disturbed, every color a ripple of energy. But here's the beautiful part, you're not just observing this from the outside. You're part of it. Every breath you take is fields rearranging, oxygen molecules meeting your cells, photons bouncing off your skin, electrons holding your atoms together. The world you touch, the air you breathe, even the thoughts in your mind are fields in motion. You're not separate from this quantum stage. You're the stage itself, playing its part in the endless performance of existence. Now, let's pause and breathe into this. Close your eyes and imagine the room around you isn't empty. It's full, not with things, but with possibility. The walls aren't solid, they're fields, waiting. The light isn't just particles moving in straight lines, it's waves of energy, fields trembling. And you're a ripple in this vast, humming sea of fields. Not a solid you, but a you made of motion, of temporary harmony, of energy finding its form. This isn't just theory. It's how the universe works. When scientists smash particles together in accelerators, they're not breaking marbles, they're stirring the fields, watching ripples transform into new shapes. When light hits your eyes, it's not little bullets of energy striking your retina, it's the electromagnetic field whispering its story to you. You are the listener. The field is the message. And every moment, you're both the ripple and the pond. So, as you rest, let this sink in, you are not a fixed thing. You are a disturbance in the fabric of existence, a brief harmony in the cosmic symphony. The world isn't made of unchanging parts, it's made of fields, of potential, of energy finding its way. And you are part of that way now. Take a slow breath in, and as you exhale, let the fields move through you. You are not separate from the quantum dance. You are the dance itself. Close your eyes for just a moment and let the world around you soften at the edges, as though you're sinking into the quietest corner of a vast, humming library. That's where the universe truly begins, not in the clutter of things you can see or touch, but in the invisible threads that stitch everything together. You've felt the weight of your own breath, the pulse of your heartbeat, the warmth of sunlight on your skin. But beneath all that, there's a deeper rhythm, a quiet symphony playing in the spaces between. This is the language of quantum fields, the unseen stage upon which all of existence performs. Imagine standing on the shore of a still pond at dawn. The water is smooth, unbroken, waiting. Then a pebble drops, a ripple spreads, catching the light, before fading into calm once more. That's not just water, it's the universe in miniature. The pond is the quantum field, the ripple is a particle, and the moment of disturbance is the spark of your awareness. The field was always there. The ripple was never separate from it. You are that ripple right now, rising and falling on the surface of something far greater than yourself. And just as the pond remains when the ripples settle, the field remains when the particles fade. You are not a solid thing. You are motion given form. Now let's step back even further. The air you breathe, the chair beneath you, the stars burning in the night, they are all made of the same invisible threads. There is no empty space, no void. Everywhere you look, fields stretch like an unseen fabric, waiting to be disturbed. Toss another pebble, and the electron field hums as an electron emerges. Toss a little harder, and a photon of light leaps into being from the photon field. These fields are not just background noise. They are the very substance of reality. The quiet hum beneath the clatter of particles. And when two ripples collide, when energy crashes together in the heart of a star or in the chambers of a particle collider, something beautiful happens. The fields rearrange, and new ripples appear, like notes blending in a symphony. An electron might become a quark. A quark might dissolve into light. It's not destruction, it's transformation. The fields rewriting themselves in endless creativity. Here is the astonishing truth: you are made of these fields. Not just your body, but your thoughts, your memories. The very act of listening to this right now, all of it, is a ripple in a vast, interconnected ocean. The electron field that courses through your nerves is the same one that binds galaxies together. The photon field that lets you see these words is the same one that carries sunlight across 100 million miles of silence. And the Higgs field, that's the molasses of the universe, the slow drag that turns light into substance, that gives you weight, that lets you stand here instead of drifting like smoke. Without it, you wouldn't exist. You'd be a fleeting thought, a whisper lost in the wind. But because the fields hold you, you are here. You are real. Let's try another image. Picture a trampoline stretched across an endless room. Its surface taut and waiting. Tap it lightly, and the ripple spreads in slow circles. Tap harder, and the waves rise and fall with more energy. Now, imagine that the trampoline itself is the quantum field, and the ripples are particles. The trampoline doesn't disappear when the ripples fade. It remains, steady, unbroken. You are one of those ripples, rising and falling on a field that stretches beyond the stars. And just as the trampoline supports every ripple equally, the fields support every particle, you, the air, the distant galaxies, all part of the same fabric. This is the quiet revolution of modern physics. The universe is not a collection of separate things, but a single, shimmering stage where everything is connected. You are not a lone marble rolling through space. You are a disturbance in a field that knows no boundaries. That means when you breathe, when you dream, when you feel the warmth of another's hand, you are touching the same fields that hum through the cosmos. There is no separation, only the illusion of it. Now, let's turn to the symphony that plays on this Schrödinger standard model, the closest thing we have to a score for the universe's music. Think of it as an orchestra tuning up before a performance. Each instrument is a particle, each section a family of forces. The fermions, the violins and cellos, the clarinets and oboes are the particles of matter. Quarks, the building blocks of protons and neutrons, are like the deep, resonant strings holding the music together. Leptons, like the electron, are the lighter notes, the quick flutters of energy. Then there are the bosons, the conductors and percussionists. Photons carry the electromagnetic force, binding electrons to atoms and letting light dance across the stage. Gluons hold quarks together inside protons and neutrons, like an unbreakable glue. The W and Z bosons conduct the weak nuclear force, the quiet but essential rhythm that powers stars and fuels the sun's fire. And then there's the Higgs boson, the humblest of all. It doesn't strike a bold note. Instead, it's the molasses, the slow drag that gives particles mass, that lets them cling together to form the world you know. 12 fermions, 4 bosons, and one field. This is the cast of characters in your body, in the stars, in every breath you take, and the symphony they play. It's been performing since the universe began, from the first flicker of the Big Bang to the quiet pulse of your heartbeat right now. The same notes have echoed through time. The Standard Model has predicted outcomes with astonishing precision. It has explained how particles behave, how forces weave together, how light bends and matter holds. It's the most successful description of reality we've ever written, a symphony that has played true for decades. But even the most perfect symphony has its silences. The Standard Model is incomplete. Gravity, the force that shapes galaxies, isn't fully part of the score. Dark matter and dark energy, which make up most of the universe, remain mysteries, like a distant choir singing just beyond hearing. It's as if you're sitting in a concert hall, listening to a masterpiece. But in the pauses, you catch the faintest whisper of another melody, something deeper, something still being written. So here's the soothing truth: for tonight you are part of that symphony. The atoms in your body are fermions, held together by bosons, given mass by the Higgs field. Every thought, every breath, every spark of consciousness is a note in this endless performance. The universe is not a machine of cold, unfeeling parts. It's a living, breathing stage where every ripple matters. And even when the notes fade, the fields remain. Even when the symphony seems to quiet, the music goes on. As you settle into rest, imagine the orchestra softening at the edges. The strings unwind, the brass mutes its gleam, the conductor lowers their baton, and the final note lingers in the air like a sigh. But the stage is still there, the fields are still humming, and you are part of the music, a ripple in the cosmic pond, a note in the universal symphony. You are not separate. You are the disturbance in the field that carries you. Close your eyes now. Feel the trampoline beneath you, steady and unshaken. Hear the quiet hum of the fields, the slow drag of the Higgs, the distant harmony of fermions and bosons playing their roles. You are here because the universe chose to ripple, and as you drift into sleep, know this: the music will always be playing. You are its latest note, and the stage will hold you until the last ripple fades. So let me take you somewhere quiet now, where the symphony of science hums softly in the background. You've heard the echoes of the universe's greatest composition, the one written in particles and forces, where every note has been tested, measured, and confirmed. And yet, even as the music swells around us, there's a whisper waiting in the pauses, a melody just beyond our hearing. That's the beauty of it. The Standard Model doesn't just explain what we see, it invites us deeper. Imagine sitting in a grand concert hall, bathed in the rich tones of strings and brass, the air alive with harmony. Every instrument plays its part with such precision that the music feels inevitable, as if it's always been this way and always will be. But listen closely in the quiet moments between movements. There's something else. There is a murmur of voices, a rhythm that doesn't quite fit. That's the universe reminding us this is only part of the song. The Standard Model has given us the Higgs boson, the players of the electromagnetic force, the strong and weak interactions, each one confirmed with breathtaking accuracy. The Large Hadron Collider hums with the energy of creation. And yet, even as it reveals the particles of light and matter, it leaves gravity untouched. The gravitons, if they exist, remain silent. Dark matter and dark energy, the unseen conductors shaping galaxies, still play from the shadows. We hear the orchestra, but the full score is still being written. And here's the soothing truth: the fact that the music isn't finished is what makes it alive. Science isn't a fixed puzzle to solve, it's a living conversation. The standard model is like a child's sketchbook, full of careful lines and bold colors, but with blank pages left for the next generation to fill. You are part of that generation. Every breath you take is woven into the same fabric. The atoms in your bones, the electrons dancing in your synapses, the photons painting sunlight across your skin there, all playing their part in this endless performance. The universe isn't a machine, it's a stage, and you're standing on it. Close your eyes for a moment and feel it. The air around you is made of particles, trillions of them, each one following rules you've only begun to understand. When you exhale, you're sending ripples through the same quantum field that held the first stars together. The symphony has been playing since the Big Bang, and it will play long after you've stepped off the stage. But tonight, as the notes fade and the conductor lowers their baton, the music doesn't end, it shifts. The crescendos soften into a lullaby, gentle and steady, carrying you into the quiet between beats. The standard model may be incomplete, but the music goes on, and you are part of its resonance. Now, let's turn to one of the most exquisite movements in that symphony: quantum electrodynamics, or QED. It's the theory that describes how light and matter hold hands across the void. Electrons and photons, particles of electricity and particles of light, engage in a silent conversation, a dance of attraction and repulsion that powers everything from the glow of a candle to the spark in your fingertips. And what's remarkable is how this conversation has been mapped with such precision that it feels almost magical. Picture this: you're at a cafe, sketching on a napkin, drawing quick lines and loops to represent particles interacting. One straight line for an electron, a wavy one for a photon, meeting at a point where they exchange a fleeting glance. These are Feynman diagrams, the playful doodles that have predicted reality with jaw-dropping accuracy. Richard Feynman, the physicist who turned quantum interactions into art, once said that nature uses the shortest possible path to get from one place to another. In QED, that means an electron doesn't just take one rotate, takes every possible path at once. Straight lines, zigzags, loops, all of them happening simultaneously, their probabilities adding up to a single, precise outcome. It's as if the universe is a vast stage, and every actor gets to play every role before the final curtain falls. The beauty of QED lies in its humility. It doesn't claim to know everything. It simply says, here is how light and matter talk, and it's so good at that conversation that its predictions match reality to staggering levels of detail. Take the magnetic moment of an electron, a tiny property that describes how it acts like a microscopic compass. Measure it in a lab, and the number you get will match QED's calculation to more than 1 part in a trillion. Imagine measuring the distance from Earth to the Moon and being off by no more than the width of a hair. That's the kind of harmony QED brings to the cosmos. But why does it work so well? Because QED embraces the fuzziness of the quantum world. It doesn't ask, what single path does an electron take? Instead, it says, add up all the possibilities. The diagrams aren't just drawings, they're a reminder that reality is a tapestry of infinite threads, each one contributing to the final pattern. And when the math is done, the numbers line up, not because the universe is simple, but because it follows rules so precise that even its chaos can be predicted. This isn't just theory, though. QED is the invisible hand guiding the technology around you. The circuits in your phone, the lasers in your DVD player, the GPS that navigates your car, all of them rely on QED's ability to describe how light and matter interact. Every time you swipe a card or watch data race through fiber optics, you're witnessing QED in action. It's the quiet architect of the modern world, and yet it remains unseen, like the foundation of a skyscraper. But even QED has its limits. It's a virtuoso soloist, dazzling in its precision. But the full orchestra is still waiting. It describes electromagnetism with unmatched accuracy. Yet gravity remains outside its score. The strong and weak nuclear forces are its companions, but they play a different tune. And though QED's calculations are nearly perfect, they sometimes produce infinity answers that make no sense unless they're carefully trimmed away through a process called renormalization. It's a bit like alchemy. Take the madness of the infinite, refine it, and what remains is a prediction that matches reality down to the smallest detail. Feynman called it a Dippy process, but it works. And that's the magic of QED. It takes the strange and makes it exact. There's comfort in that, isn't there? The universe isn't just wild and unpredictable, it's also precise, almost stubborn in its accuracy. QD shows us that even amid the chaos of quantum possibilities, there are threads of perfect harmony. A note struck in tune, a calculation matching reality to within a hair's breadth, a soloist playing flawlessly while the rest of the orchestra waits. It's a reminder that perfection isn't about grand gestures, it's about the careful, exact work of small things. So as you settle into the quiet of the night, imagine the electrons and photons around you chatting softly in the dark. Their conversations are sketched in the cosmic notebook of Feynman diagrams, each line a promise of precision. Picture the orchestra with one soloist playing beautifully, the rest holding their breath, waiting for their turn. And know this: the universe answers with a yes, a soft, exact yes, whispered through the language of particles and forces. But QED isn't the only place where quantum mechanics hums in the background. It's not confined to laboratories or particle kaleidoscopes woven into the world around us, sometimes in ways we're only beginning to understand. Take the robin on your windowsill, migrating across continents with effortless grace. Scientists believe it may navigate using Earth's magnetic field, not with iron in its beak, but with quantum entanglement in its eyes. Inside special proteins, pairs of electrons become linked, their delicate state shifting with the angle of the planet's magnetic field. The bird literally sees a pattern in starlight, guided by entangled particles, a compass painted invisible across the sky, read by a creature no larger than your hand. It's a breathtaking thought that evolution, in its quiet wisdom, has honed quantum sensors long before humans discovered the theory. When you watch a robin take flight, drifting steadily toward distant shores, imagine its eyes decoding invisible cues, the language of particles shaping its path. Quantum mechanics isn't just physics, it's biology. It's the secret hum of life itself. And plants may be part of this conversation too. In photosynthesis, sunlight is captured and funneled into chemical energy with astonishing efficiency. For years, scientists wondered how energy moves so seamlessly through a leaf, almost as if it's testing every possible path at once. Studies suggest that quantum coherence allows the plant to explore multiple routes simultaneously, guiding energy along the most efficient trail. Imagine a traveler entering a maze and somehow walking every path at the same time, choosing the exit instantly. That's the gift of quantum mechanics to a sunflower. Even your sense of smell might be tangled in this web. Some theories propose that when an odor molecule enters your nose, electrons tunnel through its slipping quantum style from one place to another. The tunneling depends on the molecule's vibrations, creating a unique signature that your brain interprets as scent. If true, then every breath you take is a quiet conversation between biology and quantum tunneling. The world is more strange and interconnected than we ever imagined. Of course, these ideas are still being tested. Not every scientist agrees on the strength of the evidence, and more experiments are needed. But the beauty of it is this: the more we learn, the more we realize how deeply quantum mechanics is woven into the fabric of life. From the migrations of birds to the photosynthesis of trees, from the precision of technology to the mysteries of our own senses, the rules of the quantum world are everywhere. And you are part of that world. So as you rest now, Feel the electrons in your body humming softly, the photons of sunlight lingering in your skin, the quantum conversations happening in every breath you take. The standard model may be incomplete, but the music goes on. And you are part of its resonance. The universe isn't just a stage, it's a symphony, and you're holding the baton. So here's the final thought tone that hums with the quiet wonder of it all. Imagine, just for a moment, a robin taking flight, its wings cutting through the air as it reads the invisible compass of the Earth's magnetic field. Not through some mechanical sense, but through a delicate dance of entangled electrons in its eyes. That tiny bird, no bigger than your hand, is carrying a secret quantum sensor, one that evolution perfected long before we even knew such things existed. And as it soars across continents, guided by patterns woven from starlight and entanglement, you're witnessing quantum mechanics in action, not in a lab, but in life itself. Now, shift your gaze to the ground, where a leaf stands basking in sunlight. It doesn't just absorb light, it chooses the most efficient path for energy to travel, testing multiple routes at once like a traveler in a maze who somehow walks every path simultaneously. That's quantum coherence at work, a wave-like spread of possibility that ensures every photon is funneled with near-perfect precision. No wasted energy, no unnecessary steps, just pure, elegant efficiency. And it's not just leaves. When you breathe in the scent of fresh rain or the warmth of baking bread, you might be experiencing quantum tunneling in real time. Electrons slipping through molecules like ghosts, their vibrations creating a signature that your brain interprets as fragrance. Every breath is a quiet conversation between biology and the strange, unseen rules of the quantum world. These aren't just theories or distant possibilities, they're threads woven into the fabric of existence. Quantum computers, still in their fragile infancy, whisper of a future where problems too vast for classical machines become solvable. Imagine simulating an entire molecule, predicting how it will behave before it even exists, designing medicines with atomic precision, crafting materials stronger than steel, lighter than air. The potential shimmers like those same constellations the robin navigates by just waiting to be reached. But here's the beauty: quantum mechanics isn't just about machines or molecules. It's about the balance between chaos and order, between randomness and reliability. At the smallest scales, the universe doesn't play by strict rules. A particle decays when it wants. A photon arrives where it pleases. An electron spins unpredictably. Yet, when you step back, the patterns hold. A million atomic decays will follow a perfect curve. A storm may bring unpredictable raindrops, but the bucket outside will always fill to the same level. This is the paradox that makes the world both mysterious and trustworthy. The universe allows spontaneity at its core, yet in the long run, the river always flows true. So as you stand here, alive and aware, remember this: you are part of it all. The same quantum rules that guide a robin's flight and a leaf's efficiency pulse through your own body. Your heart beats in a rhythm governed by probabilities. Your thoughts emerge from the tangled web of neural connections, where particles dance in ways we're only beginning to understand. And when you close your eyes tonight, imagine the steady rain of quantum randomness, the unpredictable drops, the perfect patterns. Imagine the quiet hum of the universe, where every smallest event is free, yet every grand design holds steady. This is the lullaby quantum physics sings. It's a reminder that mystery and reliability can walk hand in hand, that the tiniest moments are filled with possibility, yet the whole of creation remains unshaken. That life, technology, and the stars themselves are all singing the same quiet song. And as you listen, take heart. You are made of stardust, entangled with the universe in ways you can't yet see. The future isn't just something to chase, it's something to witness, to understand, and to embrace with open eyes and an open mind. The adventure is far from over. It's just beginning.